Well, hello there. So today what we're gonna do, we're gonna switch our gears just completely and stop talking about algorithms for a little bit, and we'll start today and continue tomorrow talking about some different computational models and what does that mean to solve a computational problem in those computational models. So today's topic is communication complexity, and it's about people or like players who are trying to figure something out. And while computations in this model are free, the communication between parties is extremely expensive. So we have, in the most basic definition, we have two players, both have some information, and they want to know something about the union of information, and then they try to talk to each other and send as few bits of information as possible to actually do stuff. Before we give some formal definition, let's talk about most basic problem in the area. It's a problem called equality. So the function equality given two inputs should output yes if x is equal to y, and no if x is different from y. So now we have the setting where so you have Alice and Bob, two traditional names for the players, and Alice possesses knowledge of some x and Bob possesses knowledge of some y. And let's say x and y both are n-bit strings. So both are just strings of n bits. And what they can now do, they can communicate. Each communication is one party sending one bit to another player, right? So let's say first Alice says something to Bob, just one bit, and then Bob says something to Alice, and then Alice says something to Bob, and then Alice says something more, and then Bob says something, and so on. So the question is how many bits of information they have to exchange to solve this problem, to find out if the inputs are actually equal to each other. All right, so one can imagine that you can do that in n+1 bit of communication. How that? Well, Alice can just send the whole x to Bob, just one bit at a time. It's an n-bit string, so she can actually send everything to Bob. All right. So, and then Bob returned to Alice the answer to the question. So Bob tells Alice if their strings are actually equal, because now he can compare them on his own and doesn't need any more communication. So he just returned the answer to Alice. So we can do that in n+1 bit. And that brings us to the most fundamental problem. The question in computer science is, can we do better? So computer science in general consists of mostly of two types of questions. We design algorithms, and then when we cannot design algorithms or communicational protocols or circuits or anything, any computational devices that can help us solve problems. So when we cannot find them, we ask a different question: can I prove that what I have is the best? Or like, what is the lower bound on the computational resources that are required by this problem? For algorithms, there are a few problems with that question, and the problem is that we don't know how to prove lower bounds for algorithms. There is this rather new area of conditional lower bounds, which allows you to give some partial answers to this question. For example, we talked about the longest common subsequence problem, and we can actually say that under reasonable assumptions, the dynamic programming algorithm for longest common subsequence is the best. The weak part is this phrase, under reasonable assumptions, because who's to say they're reasonable? We believe in them, but again, that we might be wrong on that. So the world would be still here if our assumptions were wrong, right? It's not that it's not something so fundamental that you have to have complete faith that it's true. It's just some assumption. But I'm getting in my favorite topic, so I ask you to forgive me for that. With communication complexity, everything is completely different. We actually know how to prove stuff. We actually know how to say that, hey, the equality problem doesn't actually have a better communicational protocol than we just described. So there is nothing smarter you can do rather than just Alice sending her whole input to Bob, and that's it, right? There are no tricks you can perform. Nothing would work. And what we will do, we will actually prove that this is true. So we're not only shifting gears in terms of our area of material. I also want to include at least few proofs of how to lower bound resources needed for the problem in the area. To prove that equality requires, in fact, n bits of communication, we need to introduce the protocols, like how we represent the communicational protocol. So we represent them with a tree. It's a binary tree. Not necessarily a complete binary tree, but the length of communication is the depth of this tree. So every node of this tree belongs to one of the players. So here's, let's say we have that Alice has this node, Bob has this one, Agnes has this node, and so on. Something like that. Leaves do not belong to anyone. So, and then every node also have this function so to describe the protocol, we need to know what Alice is going to say, right? So this tree we should be able to understand, like for a particular pair of inputs x and y, we need to know what the communication would look like, right? So in this node, we know that on some inputs, the very first bit that Alice is going to send is 0, and the very first bit that Bob is going to say, or that Alice is going to send, is 1. So this is kind of what is here. So this is like a function f of x, which tells us what is the first message of Alice. So then we also have the similar functions in every. So in every node we have a function that tells us what is the message by the player who owns this node. And you can tell that it's not always that like Alice sends a bit, then Bob sends a bit, then again Alice sends a bit. So it can be that after the first bit of communication, if Alice sends 0, then now it's Bob's turn to communicate. But if Alice sends 1, then she will send another message after that. It's only required that at any point they both know who is to speak. All right. So what I want to introduce now is the combinatorial rectangles corresponding to the nodes of this protocol. So I want you to consider a rectangle where all the rows are bit strings of length n, and all the columns are also correspond to bit strings of length n. So the rows of this rectangle will correspond to inputs to Alice, to different axes, and columns will correspond to different y's, or inputs of Bob, right? So what happens if when Alice sends 1 bit of communication? That means that we can color some of her rows We can color with one color all the rows where she sends 0, and with another color all the rows on which she will send 1, right? So for convenience sake, I can rearrange the rows so that it would look more like this. The order of the columns doesn't really come into play. It doesn't really matter. So we can rearrange them as we please. So I can say that my rectangle, or in this case square, is split into 2 halves, or 2 parts, right? So on top are so every input from this part, from the top part, are such that on this input, the first message of ls would be 0. And here are all the inputs. So in this half of the rectangle, we have all the inputs on which ls says 1. All right. And then we can kind of put this rectangle into this node and this rectangle into this node. So in every node of the tree that defines the communicational protocol, we can define a rectangle of, so this is like all the inputs on which are consistent, all the inputs of Alice and all the inputs of Bob that would get to this node of the protocol. So if we are here, so we have a rectangle, right? So we have a rectangle such that Alice said 0 and Bob then said 1. So we have to be in this part of the rectangle, and then because Bob was saying something, we also split this one in 2 parts, right? So we have to be from this particular rectangle in this subrectangle of the original rectangle. So this is just like all the inputs of Bob that are consistent with Bob saying 1 here, and all the inputs of Alice that are consistent with Alice saying 0 here. So if we go deeper, well, so if we are here, we have to be consistent. So Alice has to be consistent with Alice saying 1 here and Alice saying 1 here. And also Alice, so Alice has to be, if we are here, Alice has to be consistent with saying 1 here, 0 here, 1 here, and Bob has to be consistent with saying 0 here. So every time we're in a particular node, we have some set of inputs for Alice, some set of inputs for Bob's, and any pair, any combination of those things will have the same behavior from the perspective of communicational protocol, right? So, for example, the protocol we described for equality would be just, first of all, you have this like giant tree with n of depth n, just marked by Alice, where the path to the nth level of this tree just spells out Alice's input. And then we have one more layer where Bob answers if he has the same input. So now the question is, can it be that equality can be solved by some efficient protocol? So can it be that there is a protocol that is even a little bit more efficient than this trivial one is sending everything? And the answer is no. And let's see why. So suppose you have a protocol where Alice and Bob exchange less than n bit of communication. So you have a protocol tree of depth less than n. So then number of leaves number of leaves in it is strictly less than 2 to the n. All right. So now let us consider, so at every leaf here, they're supposed to know the answer. So either they know the answer yes, our inputs are equal, or they know the answer no, our inputs are not equal. So how can we use that? Well, consider a leaf of such a tree. Consider this leaf. So we have a rectangle, a leaf where they know that the answer is yes. Right? Okay. So they know that the answer is yes. So you have, again, a combinatorial rectangle that corresponds to this node. So we have all the Alices who are consistent with the path to this leaf. And you have all the Bobs who are consistent with the path to this leaf. Suppose that at least one of them has, so what is, so it has, it's a, it has a set of rows that we will call A, and we have a set of columns that we call B. So suppose A, size of A is more than 1. So this is more than, it has more than one column, or more than one row. Then it has two different inputs, x1 and x2, right? But let us consider some row in B. So then we know that for some column, for some input of Bob, so if Bob has, so we have x1, x2 in A, and we have some y in B. We know that x1 is not equal to y, or x2 is not equal to y. Why? Well, the x1 and x2 are different from each other, and we know that they cannot be both equal to y, because otherwise they would be equal to each other, right? So Alice just saw what Bob was sending her, right? And both x1 and x2 will result that they are both at this point, and they're supposed to know, Alice is supposed to know that her input is equal to Bob's input. But for one of them, it is not true. So it cannot be that size of A is more than 1. You can give a symmetric argument that size of B cannot be more than 1. So we know that if we're in a leaf, it's just a rectangle with just one row marked an A and one column marked the same A. So every leaf where the answer is yes is just a rectangle of size 1 by 1. So what's bad about it? So what does it tell us? Well, how many of those do we need? We know that for every possible A, if we give Alice and Bob, like for every possible input, if we give the same input to Alice and Bob, they have to reach some leave and answer yes. And this leave should be different for every possible input. There are 2 to the n possible inputs, so there should be at least 2 to the n possible leaves with the answer yes. And that contradicts the fact that we said, hey, let's consider the protocol of depth less than n, which has less than 2 to the n leaves. This is a contradiction. That means that no protocol for equality is able to solve, no protocol of depth less than n is capable of solving the equality problem.